Hello students. So today we are going to start the next chapter named work, energy and power. These are three very important terms in physics. As such, these words you might also be using in your day-to-day English language. But the meaning in physics is somewhat different than the common meaning that you know about these words. Like if you have read a book, you will say, if the mother asks that what work you have done, you will say, I have read this book, or I have completed 50 pages, or I have written 2 essays. But in physics, this is not work, because this is mental work. In physics, we are dealing with physical work. So we have to understand exact definition of what is work in physics. Like I would say, if a coolie is carrying a suitcase on his head and standing at the bus stop, as far as physics is concerned, he is doing no work. Let us try to understand that in physics, when we say the work is done. So work is done when a force is acting on the body. So a force should act on the body, this is first condition. Then it should cause displacement. If the displacement is not in the direction of force, then we will take the component of displacement in the direction of force. Then we say the work is done. So for a force to do work, there has to be some displacement in the direction of force. Then work done is equal to product of force and displacement in direction of force. Now force and displacement both are vectors, but when we multiply their magnitude, the work done is scalar. So such products, when two vectors are multiplied and the answer is scalar, we will be learning in vector algebra. This is called dot product. I will come into somewhat detail later on. So now the point that you should learn is that work done is equal to force multiplied by displacement in the direction of force, and work done is a scalar. So W is equal to F into displacement is S. So what would be the unit of work? So if we consider SI system, then Newton multiplied by meter, Newton meter. So this is the SI unit of work. Now Newton meter is called joule. And in CGS system, so work done would be dyne centimeter. Force is measured in dyne, displacement is measured in centimeter. So work done is dyne centimeter, which is called arc. Is it all right? So when is 1 joule of work done? So 1 joule of work is done when a force of 1 Newton displaces a body through a distance of 1 meter in the direction of force. Similarly, 1 erg of work is done when a force of 1 dyne displaces a body through a distance of 1 centimeter in its direction of force. Okay, now you will understand when I told you a coolie is carrying a suitcase on his head. So there is no displacement. The weight force is acting downward. There is no displacement down in the downward direction, upward direction. So work done is 0. If a man pushes a car and the car does not move, he is not doing work, because there is no displacement. So displacement is very important, and displacement has to be in the direction of force, or we should take its component in the direction of force. How to take the component in the direction of force we will be studying in the next slide. Is it all right? Now let us see this. isn't it? We have learned 1 joule is equal to 1 Newton multiplied by 1 meter. Now what is 1 Newton? 1 Newton is 10 raised to 5 times. And what is 1 meter? 1 meter is 100 centimeter. So if I multiply these two, I will get 1 joule equal to 10 raised to 7, and 9 centimeter is called in CGS arc. So this is how we can convert from one system to another, that 1 joule is equal to 10 raised to 7 arcs. So you should know how to calculate this. Is it alright? Now, sometimes we use a word kilojoule. Kilo means 1000. So it will be 1 kilojoule is 10 raised to 3 joule. We know that 1 joule is equal to 10 raised to 7 ergs. Bigger units are 1 kilojoule, which is 10 raised to 3 joules, 1 megajoule, which is 10 raised to 6 joule, 1 gigajoule, which is 10 raised to 9 joule. Now, work done W is equal to F multiplied by S multiplied by cos theta. See, you are applying the force in this direction. Body is moving in this direction. Then we should take the component of this displacement in the direction of force. So from here, if I draw a perpendicular to F, then this is the displacement in the direction of force. If this angle is theta, then the value of this displacement in direction of force is S cos theta. So work done is W is equal to F into S cos theta. This you should learn. That work done W is equal to F into S cos theta, where theta is the angle between F and S. So when W would be 0, if force is 0, or displacement is 0, or cos theta is 0. When is cos theta 0? Cos theta is 0 when theta equal to 90 degree. Means displacement is perpendicular to the force. Like common example of this is when a body is moving in a circle with uniform speed. So when the body is moving, if this is the radius r, body is here at some instant, then its displacement is perpendicular to this in this direction. But we have learned centripetal forces along the radius. So angle is 90 degree. So work done is 0. Now wherever may be the body, if the body is here, then this is the r, this is displacement, this is the direction of displacement, velocity, and this is direction of force, centripetal force to 90 degree. So whenever a body is moving in a circle, work done is 0, so its energy will not increase, so its velocity will not increase. Is it alright? So this is how we define work. So this is very important relation which you should learn. W is equal to F cos theta. W is equal to F cos theta. So this is very important. And in vector notation we write W is equal to F bar dot S bar. Dot means dot product. Okay. So now when a person is lifting, if a person is lifting a body, person is lifting a body. Body was here. He has lifted it here vertically. So when a person lifts a body, then what is the force acting down? mg. So what force he has to apply? mg. And what is work done? Force into displacement. So mg multiplied by h. If this displacement is h, person has lifted a body through a height h. Weight force was acting downwards, so a person has to apply that weight force which is mg and displacement is h, so work done is mgh. So whenever you are lifting a body through a height h, you are doing a work done of mgh. So where does this work done, this energy go which a person has applied in doing this work done? It gets stored in the body in the form of potential energy. So we say potential energy of a body at height h is mgh. Okay, so now we'll go to other concept. Now suppose earth is always pulling a body down. Earth is pulling a body down. But you have thrown a ball up. You have thrown a ball up. Earth is pulling it down, ball is going up. So what is the direction between displacement and the gravity weight force? Is 180 degree. What is cos 180? Minus 1. Therefore work done would be, if the ball is going to height h, so work done by gravity would be minus mgh. Because earth is pulling it down and ball is going up, so work done, you should always say work done by which force? Work done by gravitational force of earth is negative. Is it alright? So now I will prove that work done is equal to F into S multiplied by cos theta. Let us try to prove it. You see this diagram drawn in the slide. Okay, so see this diagram. Force is being applied in horizontal direction. So this is the line of force. The body is kept on an inclined plane CAB. So when I apply this force F at point A on the body moves along AC. As the body is moving along AC, displacement is AC. But as my force is horizontal, I have to take the displacement in horizontal direction. So from C, I have drawn a perpendicular to the line of action of force. So that point is B. So AB is the displacement in the line of action of force. Now if I take cos theta would be AB upon AC. I have written it here. Cos theta is equal to AB upon S. So this is my cos theta. By definition of cos theta, AB upon S. So what is AB? S cos theta. So as AB is S cos theta, what is work done? Force into displacement. So force F into displacement S cos theta. So W is Fs cos theta. So this is the derivation, that if my displacement is at an angle theta with the direction of force, then work done is Fs cos theta. Now in this case, I have taken displacement in the direction of force. I can also take force in the direction of displacement. So that is shown in this next figure. The same, force F is horizontal, displacement AC is in an inclined plane, and this displacement is S, and angle is theta between displacement vector and this force vector. So now in this case, from P, I am drawing a perpendicular in the direction of S. So this is S. So from the force, from P I am drawing perpendicular. So PA is my force. If I take now triangle P and A, triangle P and A, if I take cos theta, then this is 90 degree, hypotenuse is PF or F. Okay, so cos theta is NA, adjacent side upon hypotenuse. So my cos theta in this case is Na upon F. So I will get Na equal to F cos theta. So Na is the force in the direction of displacement. Therefore, work done is force into displacement. So work done would be F cos theta into displacement, which is F. So Fs cos theta. So I can take either force or displacement in the direction of other. The answer would remain same. So the formula is W is equal to Fs cos theta. Is it all right? Okay. Now suppose if I plot a graph, this is my displacement, this is my force, and the graph happens to be the straight line. So the force is of different magnitude as the displacement increases. Then if I want to know what is the work done, then what you should do, from this end point you draw a perpendicular to the displacement, then this area of this triangle, this area is the displacement. So the area we say under the curve and x-axis gives the displacement. So force may be a variable force. So force is like this, suppose. Then what is the work done? So what I will do, I will draw a perpendicular from here, and work done would be this area. So area under the curve, like simple case, what we are seeing is force is constant. Force is equal to 10 Newton, and here displacement is 5. So from the end point, if I draw a perpendicular, then work this area. So what this area? 10 into 5. We know work done is force into displacement. So 10 into 5, 50. So work done is equal to area under the curve and x-axis. Is it all right? So this completes about work. So now we'll go to energy. What do you mean by energy? Energy of a body means the capacity to do work. If a body can do the work of 100 joule, then we say the energy of the body is 100 joule. So its units are same as work, and it is also a scalar quantity. Is it all right? We'll be learning later on about watt, but what is 1 watt hour is also energy. Watt hour is energy, means 1 watt multiplied by 1 hour. What is 1 watt? 1 watt means 1 joule per second. So if you are doing a work of 1 joule in 1 second, then we say that power is 1 watt. So power is rate of doing work. So what is power? Rate of doing work. So power is rate of doing work. So power is rate of doing work. So power is work done upon time. So if 1 joule of work is done in 1 second, then we say the power is 1 watt. And if 1 watt is the power, means you can do 1 joule of work per second. So in 1 hour, how much work you can do? Whatever is the power, multiply by 1 hour in seconds, which is 3600. Therefore 1 watt hour is 1 watt into 1 hour. What is 1 watt? 1 joule per second. What is 1 hour? 3600. So 1 watt hour is 3600 joule. So this is the unit of energy. So 1 watt hour means you are able to do 1 watt of work in 1 hour, for 1 hour. If you switch on the light, you are switching on for 1 hour. So the energy you will get is more. Similarly, 1 kilowatt hour means 1000, we have to multiply by 1000. So multiply with 1000, so we will get 3.6 million joule. Now normally heat energy in early we were measuring in calories. Though now we say that all energy should be measured in joule, but in earlier days we were measuring heat energy in calories, and the conversion is 1 joule is 0.24 calories or 1 calorie is 4.18 joule. So these conversions also you should learn. Now in atomic physics, electrons, protons, neutrons, their energy is measured in a unit called electron volt. 1 electron volt means if the difference between 2 points is 1 volt. Suppose this is plus 1. When this is plus 1 compared to this, so if the electron is here, it will get attracted by this plus 1 volt. So when it gets attracted, it will move towards it. So when it is moving, it will gain good amount of energy. It will gain velocity, so it means it has gained kinetic energy. We will be learning about kinetic energy now. So this 1 electron volt is energy gained by electron when it gets accelerated by a potential difference of 1 volt. Is it all right? And the conversion you should learn. 1 electron volt is 1.6 10 to minus 19 joule. This will be learning how to derive this when we learn modern physics. So if you are doing any amount of work in a body, its energy will increase by that amount. And when the body does the work, its energy will decrease. Okay. Now to be more specific, 1 calorie is the heat energy required to raise the temperature of 1 gram of water through 1 degree Celsius, but to be more scientific, from 14.5 to 15.5. And this is the conversion. This I think we have studied previously also. Now, bigger units of power are 1 kilowatt, same thing, 10 raised to 3 watt, 1 megawatt, 10 raised to 6 watt, 1 gigawatt, 10 raised to 9 watt, 1 horsepower, 746. This is a practical unit, engineering unit we call it. 1 horsepower is 746 units. And smaller units are 1 milliwatt, 10 raised to minus 3 watt, 1 microwatt, 10 raised to minus 6 watt. Now, power I told you is work done upon time. What is power? F into S. So, F into S upon T. What is S upon T? That is velocity. So, power is force into velocity. This is very important, which